Good morning, good afternoon, good evening, mammals. This video is going to be for NTI day number 7, which is Thursday, March the 19th. What we're going to talk about today is the next of our trends for this unit, looking at trends on the periodic table, which is called ionization energy. What we're going to do is kind of the same thing for a lot of these trends. We'll look at just what the numbers do horizontally and vertically, because we can look at patterns and numbers even if we don't know what the numbers mean, and figure out what happens as we go left, right, and up, down on the periodic table. Then I'll go ahead and define what the trend is for you, and we'll link it to what happens to effective nuclear charge, which is going to be like our root explanation for all of these trends. And so we're going to do that today with ionization energy. What you'll need to submit on Google Classroom is the answer to question number 9 here. We'll go over it, but you'll need to paraphrase that in your own words. And then on this next page, you'll need to answer the question number 3 in your own words. And so there'll be a Google Doc provided for you to submit that, and I've placed this as a PDF inside of Google Classroom just in case you want access to it to look at it in a form outside of this video. So let's not waste any more time and get down to it. We're going to look at the pattern in the numbers first. What we see here is that as we go to the right, these values tend to increase. It isn't a perfect pattern. There are a few exceptions. Sorry. We've got a gap in the trend right here, where when we go to the right, the numbers actually decrease. This exception isn't going to be important. It's not going to be like on your test or anything. I just want you to know that it's out there so that if you see a data set and it isn't perfect, you know what's going on. Okay, so now let's look at what happens when we go down. When we go down, the numbers actually decrease. So I'm going to make another arrow up here. I'm going to point up because this is the direction that they increase. And if we treat this just like we did effective nuclear charge, I can think about corners. Down here in this corner is my lowest ionization energy, and up here in this corner is my highest. We do have some exceptions to the vertical pattern also. If you look along between rows 5 and 6, we get a series of elements where instead of decreasing, they increase. Again, that's not going to be an important exception for you guys to know. The reason it's there is because between the 5th row and the 6th row, for the first time, we've added the F block, and that sort of interferes with things and causes there to be an exception. So for right now, just know that this increases as you go up and to the right, and we won't worry about any exceptions. Some of our later trends there's an exception over here with the noble gases that we have to worry about, but this one isn't one of them. Okay, let's look at the actual definition about what this is talking about. Ionization energy is the energy required to remove an electron. I like to think of it in terms of if I was buying an electron from one of these atoms, how much would I have to pay for it? So we can see that elements in this corner ask for a lot of energy to buy one of their electrons versus elements down here. And kind of an easy way to think about that is if I'm francium and I lose an electron, I become like a noble gas and reach a noble gas state. And that's kind of a good day for me. So these guys are over here like, all right, I'll lose an electron. That helps me out. Whereas atoms over here, their best path to become like a noble gas is to gain an electron. So they really, really don't want to lose it. But let's get a better answer and think of it in terms of effective nuclear charge. So when effective nuclear charge is high, that means these atoms have a high attraction for their electrons. So it makes sense that if they are very attracted to their electrons, it's going to be difficult for those electrons to be removed because you've got more attraction that you have to overcome, which is going to require more energy. So what I'm looking for you guys to turn in as evidence that you paid attention to this is just your paraphrasing of what I just went over. Okay, let's go to the back side. The back side includes what are known as multiple ionization energies. And these are simply the energies to remove additional electrons. So first ionization energy is the energy to remove the first electron, and then the second, and then the third, and then the fourth, and then the fifth. And what you should notice is that the ionization energies always increase as you go from the first to the second to the third. The price always gets more and more and more. So we can look at it's 520, then it's 7,000, then it's 11,000 something. But it doesn't increase in kind of an even fashion. And we're going to be looking at where these elements have a large jump in the energy required. So I'm going to do only some of these elements, the elements that would tend to want to become a cation. So I'm going to look at, actually not that many, I'm going to look at these four, and then I'm going to look at these four right here. And I'm going to find the place where their energy increases the most. So what I'm doing is I'm finding the difference between these numbers and the difference between these numbers and looking where it increases the most. This is a bigger increase than 7,000 to 11,000. Here's the biggest increase. 3,000 to 25,000 is the biggest increase for boron. And then 6,000 to 37,000 is the biggest increase. Makes kind of like a stair-step pattern. And then lo and behold, it does the same thing here. So there's a reason for this, and it relates to their valence electrons. Lithium has 1, beryllium has 2, boron has 3, carbon has 4, and the same thing here. This large increase happens after you're out of valence electrons. So this one was valence, big increase. These two are valence, then a big increase. These three are valence, and then a big increase. These four are valence, and then a large increase. So if you spot where the increase happens, you know that before the increase, that was removing valence electrons. And after the increase, you're now removing inner electrons. Let's look at that as a picture, make it a little easier to see. So here's sodium. This first electron, first valence electron, it sees 11 attractive protons, and it sees 10 inners. So it's actually got kind of a fairly low effective nuclear charge because it barely sees more attraction than it sees repulsion. So this electron comes off very easily. It's gone. Now the next ones that we're going to be removing, we're going to be trying to remove some inner electrons. We're going to be removing from this 2p. This electron, it still sees 11 attractive protons. But now since it's an inner electron, it doesn't see the other inners on its same shell. It just sees these guys, the ones that are closer to the nucleus. So now it only perceives 2 inners. So now the effective nuclear charge has gone way, way up for this next electron because it's closer to the nucleus and feels more attraction. And so we get a large increase between the first and the second. For magnesium, similar thing. It's just now we have 2 electrons that have to be removed. And so these 2 electrons come off pretty easily because they see 12 protons and 10 inners. So same thing. They don't have a super high effective nuclear charge because their attraction isn't that much bigger than their repulsion. Then, after we've done that, to remove this next electron, the same thing here. We would see 12 attractive protons, but only 2 inners. So it's going to be much more difficult to remove. And so that's why the large increase happens when you've run out of valence electrons. So if I graphed this, I would see something like, if these were some points for ionization energies, I would see, okay, I've got a large increase in between these two. And so that means these guys were valence electrons, and now I'm starting to remove my inners. So I could look at this and say, whatever element this is, it has 2 valence electrons because we look for a large increase. And on test questions, you'll either be looking for where the large increase occurs using numerical data or graphically. So the last question that you need to answer is to paraphrase in your words why there's this big increase after you've run out of valence electrons. So, as always, if you've got any questions, need help submitting anything or answering this, hit me up on Remind or on Google Classroom, and look out for yourself and others, practice good hygiene, and I'll see you on the flip side.